NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
The map was a lie. For years, scientists imagined the solar system wrapped in a neat, protective shield of energy. A smooth boundary carved by the sun's magnetic field. But Voyager's new data shattered that idea. NASA has now confirmed the solar system isn't round at all. It's distorted, twisted, and misshapen in ways that leave scientists deeply unsettled. This is what Voyager found, and why it changes everything we thought we knew. Voyager's mission beyond the planets. When NASA rolled the dice on Voyager, they weren't just planning a science mission. They were aiming for something the universe only allowed once in a lifetime. In the late 1970s, the giant planets lined up in a rare way that happens only once every 175 years. With that alignment, a spacecraft could steal speed from one world and slingshot to the next. Jupiter, then Saturn, and if the math worked, all the way to the outer ice giants. The trick meant they didn't need mountains of fuel. They just needed the courage to take the shot. Voyager 2 lifted off first on August 20th, 1977, followed by Voyager 1 on September 5th. The original mission was bold but simple. Fly close to Jupiter and Saturn, map their systems, and maybe, just maybe, push farther if the timing held. What followed was history. Voyager 2 became the only spacecraft ever to visit Uranus in 1986 and Neptune in 1989, ticking off every giant planet in the solar system like stamps in a passport. Decades later, the twins are still going. They are so far beyond the worlds they once photographed that even light itself, traveling at 186,000 miles per second, takes almost a full day to cross the distance. To put that in perspective, news reports working with NASA's numbers now place Voyager 1 at more than 15 billion miles from Earth, and Voyager 2 at more than 13 billion miles. Both are in interstellar space, beyond the reach of the sun's direct wind, yet still whispering back data. Each craft is no lightweight toy. A Voyager tips the scale at about 1,592 pounds, about the size of a small car. The most recognizable feature is the white dish-shaped antenna, 12 feet across. That big dish is the reason we can still hear from them. It beams a thin radio stream back toward Earth on a channel called X-band at around 8.4 gigahertz. Back in the planetary flybys, the data rate could reach a few kilobits per second. Out in the dark now, the signal is so faint that NASA's Deep Space Network is catching energy measured in 10 quadrillionths of a watt. That's less than a flicker of a flicker, yet still readable across the stars. In the early days, the probes also used a lower frequency S-band for engineering signals, but that mode was shut down once the planetary tour was finished. Today, every scrap of communication depends on that 12-foot dish and the X-band carrier. Power comes from something that feels straight out of science fiction. 3 nuclear batteries on each craft, officially called radioisotope thermoelectric generators, or RTGs. There are no moving parts. Each RTG turns heat from plutonium-238 into electricity. At launch, every Voyager's trio of generators produced about 470 watts. Each year, the output slips by a few watts as the fuel cools and the devices age. That steady fade is why NASA has spent years shutting off heaters, backup circuits, and eventually even science instruments, stretching every watt to keep the mission alive. Quiet discipline, not flashy hardware, is the reason these probes still run. The real treasure now isn't photographs. The cameras were turned off long ago. What remains is a compact suite of instruments built to sense the invisible. Take the Cosmic Ray Subsystem, or CRS. Imagine it as a sentinel that counts the most energetic particles in the universe, electrons and atomic nuclei traveling so fast they can punch straight through metal. CRS measures how many of them are out there, how energetic they are, and even what elements they came from. That's how scientists track the harshest radiation bombarding our cosmic neighborhood. Just below that energy scale is the Low-Energy Charged Particles Instrument, or LECP. If CRS is the high-end bouncer, LECP is the wide-ranging doorman. It covers the middle ground between the sun's gentler solar wind and the most violent cosmic rays. LECP doesn't just count particles. It can tell their energy and, importantly, the directions they arrive from. That directional data is like a weather map. It shows gradients, flows, and boundaries, whether the particles come from the sun, a planet's magnetic bubble, or the great unknown outside. Then there's the magnetometer, MAG. This instrument is the compass that never stops writing. It records both the strength and the direction of magnetic fields. On the planet flybys, MAG revealed which worlds had their own magnetic shields, and how those fields tangled with moons and rings. Out in deep space, MAG keeps a running log of how the sun's magnetic influence weakens with distance, and what the background field of the galaxy looks like when the sun's pull finally fades. The Plasma Wave Subsystem, PWS, doesn't see, it listens. Space may look empty, but it is never silent. When charged particles move through magnetic fields, they create faint electrical oscillations. PWS detects those oscillations as tones, ranging from a few cycles per second to tens of thousands. By measuring those tones, scientists can calculate how dense the sea of electrons is around the spacecraft. In other words, if you know the pitch of the plasma's song, you know how crowded the electrons are without touching them directly. Another key tool was the Plasma Science Instrument, PLS. This one didn't just infer, it measured directly. It sampled the solar wind itself, reading the speed, temperature, density, and direction of the charged particles blowing outward from the sun. On Voyager 1, PLS was retired in 2007 as the readings degraded, but on Voyager 2, it ran longer and filled in the story. Even though both PLS units are now shut down to save power, the data they returned built a decades-long baseline for how the solar wind behaves as it stretches into the void. Guiding all of this is a quiet but vital brain, the Attitude Control System. Its only job is to keep the 12-foot dish pointed home. The system uses small thrusters to nudge the spacecraft, turning the whole body just a few degrees when needed. That steady alignment is the only reason Earth can still hear the faint whispers of particles, fields, and plasma across more than 12 billion miles. But it wasn't the planets that made Voyager's biggest discovery. It was the edge of the solar system itself. The heliopause, our solar system's outer shield. The sun is more than a burning ball. It's an engine that blows. From its outer atmosphere pours a constant stream of charged particles, the solar wind, racing outward at anywhere from 200 to 500 miles per second. This flow drags the sun's magnetic field with it and inflates a giant bubble around everything we know. That bubble is called the heliosphere, and its skin is the heliopause. The heliopause is where the sun's push finally balances against the thin gas and magnetic pressure of the galaxy outside. Inside the bubble, the sun still runs the show. Step beyond it, and the very local interstellar medium, what scientists call the VLISM, takes control. In plain terms, The heliopause is the border where the sun's influence ends and the galaxy begins. But reaching that border is not simple. As the solar wind streams outward, it eventually hits a slowdown zone known as the termination shock. Here, the wind slams from supersonic to subsonic speeds, the same way air piles up behind a jet's shock cone. Beyond that sits the heliosphere, a restless zone where the slowed wind churns, heats, and twists on its way to the edge. Only after that gauntlet do you reach the heliopause, the true dividing line between the sun's plasma and the plasma of the galaxy itself. That whole sequence, solar wind, termination shock, heliosphere, then heliopause, is how scientists describe the layered edge of our home in space. For a long time, the public image of this frontier was simple. Textbooks and posters showed the solar system wrapped in a neat round bubble, like a soap sphere glowing in the dark. Even in research circles, early diagrams often kept that smooth outline, while scientists debated whether the sun's bubble stretched into a long, comet-like tail or stayed more compact. Those sketches helped people picture the idea of a boundary, but they were too perfect for the messy physics actually happening at the edge. So why did that tidy picture stick around for so long? The answer is distance. The heliopause is unimaginably far away, and it doesn't shine in visible light. You can't just snap a picture of it with a telescope. So why should anyone care about this distant frontier? Because it does more than mark a line in space. It acts like a filter. The galaxy is full of dangerous, high-energy particles called cosmic rays. The heliosphere can't block the most powerful ones, but it does scramble and soften part of that incoming storm before it reaches Earth. The effect even changes with the sun's 11-year cycle of activity, waxing and waning like a cosmic rhythm. Picture it as a storm door, not a bunker. It doesn't shut everything out, but it reshapes what gets through. Without that protective bubble, life on Earth would be battered by an even harsher rain of radiation. For decades, it was just theory, drawn in models and diagrams. But when Voyager crossed the real thing, it shattered the picture we thought we knew. The bubble, it turns out, isn't round at all. Voyager's alarming readings. When the first probe finally hit the border, it didn't look anything like a neat one-size-fits-all shell. Voyager 1 made the leap on August 25, 2012, at about 121 to 122 astronomical units from the Sun. That's roughly 11.3 billion miles. The date wasn't announced right away. Confirmation came months later, in April 2013, when its plasma wave subsystem picked up a clear whistle at about 2.6 kilohertz. That tone, caused by the density of charged gas around the spacecraft, mapped to about 0.08 electrons per cubic centimeter, the exact density expected in interstellar space, not inside the sun's bubble. Space had literally rung like a bell. That sound, recorded by University of Iowa physicist Don Gurnett and his team, was the smoking gun proving Voyager 1 had crossed the line months earlier. 6 years later, Voyager 2 reached the same frontier, but the story unfolded differently. On November 5, 2018, it crossed at about 119 astronomical units, or roughly 11.1 billion miles. Unlike its twin, Voyager 2 still had its plasma science instrument alive and working, and that changed everything. As the spacecraft crept toward the border, its detectors showed the solar ions thinning out and dropping sharply, while particles from the galaxy outside surged in. That flip was a clean fingerprint of the edge. Then, just past the line, Voyager 2's plasma wave instrument gave a solid density reading of about 0.039 electrons per cubic centimeter on January 30th, 2019, measured at 119.7 astronomical units. Interstellar space confirmed. Now here's where things got interesting. If the heliopause were a perfect uniform bubble, both probes, flying out in different directions, would have met it at about the same distance from the Sun. They did not. Voyager 1 crossed farther out, at about 121 to 122 astronomical units, while Voyager 2 made the jump at about 119 astronomical units. That may sound like a small mismatch, but in scientific terms, it was huge. It proved the edge wasn't a clean sphere. It bulges here and presses in there, like a balloon dented on one side. Voyager 1's crossing also had its own twist. Before the plasma ringing proved the electron density outside, its other instruments noticed something strange, a stagnation region. For several astronomical units, the local plasma flow slowed to nearly nothing, as if the wind had hit a dead calm. The data puzzled the team so much that they held back from calling it interstellar until the density proof finally came. Voyager 2, by contrast, gave clarity without hesitation. Its plasma instrument could directly measure the speed and temperature of the charged gas. Right at the border, the outward flow from the Sun slowed towards zero, while the particle mix flipped unmistakably from solar-born to galaxy-born. The magnetometer also recorded a stronger, steadier magnetic field just beyond the line, another signature of stepping outside. Together, the instruments painted a crisp, undeniable picture. Those differences mattered. Put side by side, Voyager 1's crossing looked messy, drawn out, with a thick transition zone before the final step. Voyager 2's looked cleaner, a sharper boundary. The contrast made the shape of the heliopause clear. It wasn't a smooth shell. It was an uneven shield, compressed and stretched in different directions, with a texture that depended on where you hit it. The scientists who had waited decades for this moment felt the weight of it. Ed Stone, the longtime Voyager project scientist at Caltech, described the two crossings as a cosmic shoreline, two tiny but priceless pinpricks of truth on a map that had always been drawn in guesswork. And John Richardson at MIT, who led the plasma science team, reiterated why Voyager 2's numbers mattered so much. The interstellar wind distortion. The reason that bubble looks dented and uneven is simple. The solar system isn't drifting lazily through calm waters. It's sailing into a headwind. Out there, a faint galactic breeze of gas and dust streams past the Sun at about 51,000 miles per hour. That breeze isn't alone. Woven through it is a magnetic field from the space between the stars. Together, this wind and its invisible field lean on the outside of the Sun's bubble, pressing and shaping it. That pressure is the reason the heliosphere, the vast shield that surrounds us, can never be perfectly round. NASA's IBEX spacecraft helped lock in the number, measuring incoming neutral helium near Earth, and showing that the interstellar wind hits us at about 23 kilometers per second. It's the galaxy ramming our front gate. Magnetism is where the real muscle comes in. By earthly standards, the local interstellar magnetic field is tiny, just a few millionths of a Gauss, or about 0.3 to 0.5 nanotesla. But stretched across billions of miles, that's more than enough to reshape the skin of our solar system. And it doesn't arrive head-on. Instead, it's tilted by about 20 to 30 degrees compared to the flow of the wind. That angle means the field can't simply cut through. It drapes over the nose of the heliosphere, piling up like fabric against the bow of a ship. The added magnetic pressure squeezes the nose inward, while the sides and the downwind regions relax farther out. Put wind and tilted magnetism together, and the geometry is simple. You don't get a perfect circle. You get a squashed, uneven shield. Voyager's data confirmed that squeeze in ways no diagram could. When Voyager 1 stepped outside the Sun's bubble, its magnetometer, led by Leonard Berlage, picked up the field jumping from about 0.2 nanotesla inside to about 0.4 outside. And it stayed there, proof that the field had draped and strengthened around the heliosphere's nose. Voyager 2's crossing years later showed the same story with a twist. It found a thinner, simpler boundary, a stronger interstellar field just beyond it, and even a magnetic barrier on approach, evidence that the external field shapes the edge differently depending on the direction you take out. But more recent, data-driven simulations say otherwise. Many point to a shorter, squashed structure. One especially bold model, championed by Merav Ofer and her team at Boston University, describes a deflated croissant. In this version, the Sun's twisted magnetic field funnels plasma into twin outflows, while the interstellar field squeezes from the nose. The result is a structure with two pinched lobes, instead of one neat bubble or one long tail. Some researchers argue for a teardrop shape, others for variants of the croissant, but across the debate, one truth stands out. The heliosphere is not round, and that distortion carries shocking implications for Earth. Radiation leaks into the solar system. As we said before, the heliosphere isn't a solid wall. It's more like a storm door. It filters and reshapes the cosmic rays flying through our part of the galaxy, but it can't keep out the hardest, most energetic ones. Voyager's data revealed that those cosmic rays don't all fight through the same way. Some leak in more easily through weak spots in the shield. Right after crossing the border, Voyager 1 started logging the raw cosmic ray spectrum in interstellar space, down to just a few million electron volts per particle. That gave us a clean baseline, the storm outside the shield before the heliosphere does any filtering, and the pattern wasn't smooth. Voyager recorded long stretches, sometimes about 100 days, sometimes more than a year, when particles coming from directions sideways to the magnetic field dipped, while other directions barely changed. That direction-dependent behavior is anisotropy. In plain terms, it means the shield is uneven, with preferred entry lanes where high-energy particles slip through more easily. So what makes those weak spots? Some wonder if these aren't just weak spots, but cracks, gateways where alien forces or unknown physics press against our shield. They could be scars on the edge of the solar system, hinting that something vast and unseen is testing the wall that keeps us safe. But the more grounded explanation is just as fascinating. The likely culprit lives right at the border. The Sun's magnetic field pushes outward. The galaxy's field presses back. Where they rub together, they can tear and reconnect. Magnetic reconnection. Picture two tangled fishing nets colliding. Some knots snag, rip, and restitch, opening holes between them. Along those temporary connections, charged particles travel much more easily, sneaking through the barrier. Models built to match Voyager's particle data describe a porous, layered edge full of these reconnection zones. Today, reconnection isn't treated as a side note. It's seen as a central piece of how the heliopause really works. So why does this matter here on Earth? Because even tiny changes in what gets through can have real effects. Airline crews who spend long hours on polar routes already log measurable radiation doses from cosmic rays, high enough that regulators in the United States require training and tracking of exposure. Satellites and high-altitude electronics face another issue: single-event upsets, where one cosmic ray flips a bit in a computer system. Engineers design around it, but when the rate of incoming particles changes, so does the rate of those glitches. This isn't doomsday, it's a reminder that our shield is not steady. It breathes, it leaks, and sometimes it opens wider than we'd like. The mystery of the cosmic ribbon. Here's where the story takes a turn. Voyager's data revealed something nobody expected. A glowing ribbon of energy stretched across the sky. And NASA's IBEX spacecraft, the Interstellar Boundary Explorer, was the one that made it visible. Back in 2009, IBEX started piecing together the first full-sky maps of particles called energetic neutral atoms, or ENAs. These are created at the edge of the solar system when hot, charged particles collide, steal an electron, and suddenly turn neutral. Once that happens, they're free to fly in straight lines, and some of them reach us here on Earth. IBEX caught those particles and turned them into a global map, and the result stunned scientists. Instead of a simple glow, the sky lit up with a narrow band, almost like a giant arc drawn around the solar system. This band stretched more than 300 degrees across the sky, about 20 degrees wide, and it was 2 to 3 times brighter than the surrounding background. Nobody had predicted it. The team gave it a name that stuck: the ribbon. IBEX revealed the ribbon, but Voyager helped explain what it meant. When Voyager 1 crossed outside the Sun's protective bubble, its magnetometer measured the interstellar magnetic field, the galaxy's own magnetic influence. It found the field was steady at about 0.4 nanotesla, and more importantly, its direction matched what IBEX had suggested. That was the breakthrough. The ribbon shines brightest in directions that are at right angles, perpendicular, to this interstellar field. Think of it as a luminous contour sketched out where the galaxy's magnetic field wraps over the Sun's bubble. So why do ENAs reveal that contour? Because they remember the path they came from. When an ion near the boundary becomes neutral, it's no longer steered by magnetic fields. It just shoots off in a straight line, carrying its travel direction with it. IBEX has 2 detectors, IBEX low and IBEX high, that capture ENAs across a range of energies, from a few electron volts up to about 6,000. By rebuilding where they came from, IBEX drew the ribbon exactly where you'd expect if the magnetic field was draping over the heliosphere. And here's something even stranger. The ribbon isn't frozen in place. Over more than 10 years of IBEX observations, its shape stayed fixed, but its brightness rose and fell in rhythm with the Sun's activity cycle. The brightness changes showed up only after a delay. The time it takes the solar wind to race outward, interact at the edge, and then send ENAs flying back to Earth. That delay became a natural clock, letting scientists test how particles circulate beyond the Sun's reach. One big question remained. Where exactly is the ribbon? Inside the bubble or outside? Scientists used a clever trick. By observing the ribbon from opposite sides of Earth's orbit, they measured its tiny apparent shift, a method called parallax. The result placed at least part of the ribbon about 140 astronomical units away, just beyond the heliopause. That's exactly where the interstellar magnetic field should be wrapped most tightly around the heliosphere. But what makes it so bright? The leading idea is called the secondary ENA process. Here's how it works. Solar wind particles first become neutral atoms, then get reionized beyond the heliopause, are bent by the interstellar magnetic field, and finally exchange charge again to become neutral a second time. That second generation of ENAs flies back toward Earth, brightening the ribbon in just the right directions. And the ribbon may be a clue to an even stranger discovery. Hints of a hidden structure beyond our solar system. Voyager data suggests the heliosphere isn't steered only by the sun. Once the probes crossed the line into interstellar space, they began picking up clues that pointed to something far bigger shaping our neighborhood. The first clue was a sound. In 2017, Voyager 1's plasma wave subsystem detected a faint, steady tone in the void, a background hum. That hum was tied to the frequency of electrons moving through the gas outside our bubble. By tracking the pitch, scientists could measure electron density every few days as Voyager drifted farther out. A team led by Stella Ocker, with Don Gurnett and Bill Kurth, stitched together a continuous record across billions of miles. What they saw wasn't silence, and it wasn't random. It revealed ripples and compressions in the gas that came not from the sun, but from the galaxy itself. Those numbers painted a picture of a background set by the Milky Way. Right after crossing the boundary, Voyager 1 measured densities around 0.08 electrons per cubic centimeter. Then, in 2020, when the spacecraft was about 149 astronomical units out, roughly 13.9 billion miles, a huge pressure wave rolled through. The density jumped to about 0.15 and stayed there, steady for years. That kind of consistency showed Voyager wasn't moving through emptiness. It was plowing through a medium shaped on galactic scales, far beyond the reach of solar winds. When you zoom out, the larger setting becomes impossible to ignore. The sun sits inside the local bubble, a vast cavity about 1,000 light-years across, carved by ancient supernova explosions. Using star maps from the European Space Agency's Gaia mission, astronomers Catherine Zucker, Alyssa Goodman, João Alves, and their colleagues built a three-dimensional map of this structure. They showed that many nearby young stars sit right on the bubble's expanding shell. That shell stretches about 540 light-years in radius and is still slowly expanding at several miles per second. In other words, the environment shaping our heliosphere is already written into the Milky Way's history, and our bubble has to bend to it. Some scientists speculate that Voyager's data might be showing us more than just background numbers. Out beyond the sun's reach, its readings could be hinting at hidden structures in the interstellar medium, thin filaments, clumps of gas, even faint currents twisting through the void. And there's an even bolder idea. If dark matter really does break apart or collide from time to time, it could leave behind a trace of low-energy particles. Voyager, sitting outside the sun's bubble, may be one of the few instruments in history able to catch those signals. None of this is confirmed, but if even part of it is true, then our solar system isn't shaped by the sun alone. It's being influenced by forces that belong to the galaxy itself. The shocking implications. So here's the truth staring us in the face. The solar system isn't wrapped in a neat, round bubble. It's more like a shield that flexes, breathes, and sometimes even buckles under the pressure of the galaxy around us. That realization flips the old picture of a fixed protective shell into something far less comforting. What we actually live inside is a moving border whose strength and shape can shift. It also changes the way we think about galactic weather. For decades, the phrase sounded abstract. Now it's something we actually have to forecast, the same way Earth tracks hurricanes. That's why NASA is preparing to launch the Interstellar Mapping and Acceleration Probe, or IMAP. It'll sit at the Sun-Earth L1 point, staring straight at the heliosphere's edge. IMAP's job is to chart how the boundary swells and contracts with the solar cycle, and to turn that knowledge into practical, real-time awareness for spaceflight and sensitive electronics. Think of it as the first weather satellite for the very edge of home. And that's only the beginning. The next logical leap is a mission designed to leave the bubble entirely on purpose. Engineers have drawn up plans for an interstellar probe, built to sprint hundreds, maybe even 1,000 astronomical units into the galaxy itself. Out there, it could measure the pressure, fields, and currents directly, instead of guessing from inside. If it launches in the 2030s, it would transform what Voyager discovered by accident into a continuous map of the forces shaping our cosmic neighborhood. Put simply, Earth isn't sitting under a perfect dome. We're tucked inside a warped, leaky shield, pressed by forces far larger than our star. That shifts our place in the Milky Way, from cozy residents of a quiet bubble to tenants on the edge of ever-changing galactic weather. And it took 2 battered spacecraft, launched nearly 50 years ago, to reveal that truth. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.